If the saturated steam produced in a boiler is exposed to a surface with a higher temperature, its temperature will increase above the evaporating temperature. The steam is then described as superheated by the number of temperature degrees through which it has been heated above saturation temperature. Superheat cannot be imparted to the steam while it is still in the presence of water, as any additional heat simply evaporates more water. The saturated steam must then be passed through an additional heat exchanger. This may be a second stage of heat exchange in the boiler or a separate superheater unit, as in this example. The primary heating medium may be either the hot flue gas from the boiler or may be separately fired. Superheated steam has its applications in, for example, turbines, where the steam is directed by nozzles onto a rotor. This causes the rotor to turn. The energy to make this happen can only have come from the steam. So, logically, the steam has less energy after it has gone through the turbine rotor. If the steam was at saturation temperature, this loss of energy would cause some of the steam to condense. Now, as turbines have a number of stages, the exhaust steam from the first rotor will be directed to a second rotor on the same shaft. This means that saturated steam would get wetter and wetter as it went through the successive stages. Not only would this promote water hammer, but the water particles would cause severe erosion within the turbine blades. The solution is to supply the turbine with superheated steam at the inlet and use the energy in the superheated portion to drive the rotor until the temperature-pressure conditions are close to saturation, and then at this stage exhaust the steam. Another very important reason for using superheated steam in turbines is to improve thermal efficiency. The thermodynamic efficiency of a heat engine, such as a turbine, may be determined using one of two theories: the Carnot cycle or the Rankine cycle. The Carnot cycle, where the change in temperature of the steam between the inlet and outlet is compared to the inlet temperature. The Rankine cycle, where the change in heat energy of the steam between the inlet and outlet is compared to the total energy taken from the steam. To better illustrate these important concepts, let's take a look at the following example. Here, a turbine is supplied with superheated steam at 90 bar absolute and 450 degrees Celsius. The exhaust is a saturated steam at 0.06 bar absolute, a saturated temperature of 36.2 degrees Celsius, and 10% wet, so with a dryness fraction of 0.9. Now, the values which will be used for the temperature and energy content in these examples are from steam tables and are as follows. Let's determine the Carnot efficiency. The Carnot efficiency can be calculated as follows, where T sub inlet is the temperature at the turbine inlet, in this case 723 Kelvin. T sub outlet is the temperature at the turbine exhaust, in this case 309 degree Kelvin. We plug in our variables for a result of 0.2%. Okay, let's now determine the Rankine efficiency. This can be done using the formula shown now on screen, where H sub inlet is the heat at the turbine inlet, H sub outlet is the heat at turbine exhaust, and H sub cond is the sensible heat in the condensate. H sub inlet is 3256 kJ per kilogram, obtained from the superheated steam tables. H sub outlet equals the heat in steam plus the heat in water, since there is a mixture of saturated steam and condensate. The heat in steam at 0.06 bar absolute is 2415 kJ per kilogram. The heat in water at 0.06 bar absolute is 152 kJ per kilogram, obtained from the steam tables. However, since at the exit the steam has a dryness fraction of 0.9, then the actual heat in the steam at the exit is 0.9 times 2415, and the actual heat in the water is 0.1 times 152. So a total of 2188.7 kJ per kilogram. Lastly, the sensible heat in condensate equals 152 kJ per kilogram, as obtained from the steam tables. Therefore, the Rankine efficiency is 34.4%. Examination of the figures from either of the cycles indicates that to achieve higher efficiency, the temperature or energy at the turbine inlet should be as high as possible. This means as high a pressure and temperature as is practically possible. Superheated steam is the simplest way of providing this. In addition, the temperature or energy in the exhaust of the turbine must be as low as possible. This means as low a pressure and temperature as is practically possible. This is normally achieved by a condenser on the turbine exhaust. Now, it is important to note here that the figures calculated in this example are for the thermodynamic efficiency and must not be confused with mechanical efficiency. Although the efficiency figures appear to be very low, they must not be viewed in isolation, but rather used to compare one type of heat engine with another. For example, gas turbines, steam engines, and diesel engines.